So, let's look at a molecule with 3 carbons. And the first carbon on the left is bonded to random generic groups. So we'll just use placeholders for those. And we typically use R as a placeholder. Typically R represents an alkyl group, so just a carbon-hydrogen group. So we don't have to draw it, but we'll just indicate that it's there. What we're really interested in are the hydrogens on this molecule. So there's 1 hydrogen bonded to the second carbon, and there are 3 hydrogens bonded to the third carbon. Now, looking at these hydrogens, we have these yellow highlighted hydrogens. Those are all the same, essentially. So if a base came in and took one of those yellow hydrogens, it doesn't matter which one of the yellow hydrogens it takes because they're all very similar. However, the hydrogen on the second carbon is different. So I'll highlight that in a different color. All right, so the next step is to show the conjugate bases for these different hydrogens and their removal from the molecule. So let's say that a base comes in and removes the green hydrogen. So we'll subtract that hydrogen from the molecule. We would end up with let's see, this molecule here, and a lone pair would be left on the central carbon. Now, that carbon is gaining an electron in that process, so it becomes negatively charged. And now let's look at what happens if we remove a yellow hydrogen. So this time, that central carbon maintains its hydrogen, but the carbon on the right has lost a hydrogen. But it's gained an electron, so now it is negatively charged. Okay, so now we need to determine, is the green hydrogen more acidic or is the yellow hydrogen more acidic? And we're going to figure that out by comparing those conjugate bases. Okay, so let's step through cardio. So 1, C stands for charge. Do we have the same charge or different charges? The same charge. Okay, so we'll move on to number 2. A is for atom. Is the charge on the same type of atom or different types of atoms? The same types of atoms, carbons. Okay, so we can't really tell the difference yet. Let's look at the third letter in cardio, which stands for resonance. Are there resonance structures? Well, the first conjugate base, where we lose a green hydrogen, does not have any resonance structures. Remember, a lone pair or a negative charge has to be next to a single bond, which is next to a pi bond. But in this case, the negative charge is right next to a pi bond. So no resonance exists there. But let's look at the second structure. Can we move electrons around and form a resonance structure? Yes, we can. So this lone pair can move down to create a double bond, And that will create a Texas carbon, so we'll have to move these pi electrons over. But what that tells us is that the negative charge is shared between two carbons. Okay, so let's actually draw that resonance structure. So let's see, I'm going to make some room. So I'm just going to erase my cardio stuff here. Put brackets around that structure. Okay, so if we move those electrons around, we'll have a double bond on the right-hand side this time. And then we'll have a negative charge on the carbon on the left. Okay, so there is resonance for that second conjugate base, which means it's more stable, right? So if the second conjugate base is more stable, which hydrogen is more acidic? The green hydrogen or the yellow hydrogen? The yellow hydrogen is more acidic. Okay. So let's draw this in red, and we'll say more acidic next to those yellow hydrogens. So in an acid-base reaction with this molecule, the base is going to attack one of the yellow hydrogens first. And it will remove a yellow hydrogen because it is more acidic or more easily lost. And the reason that the yellow hydrogen is easier to lose is because the conjugate base in that situation is more stable. And remember, molecules are always trying to become as stable as they can be. So again, that yellow hydrogen is easier to lose. All right. Oops, I went backwards. Now, if you want more practice with this, I recommend trying Skill Builder 3.9 on page 114 in the 3rd edition of the textbook. Okay, let's do another problem. So let's look at the following alcohol. So we have an OH group there. And this is the bond line structure, and normally we don't show the hydrogens on the carbons, but this time I am going to show the hydrogens so that we can try to determine which one is the most acidic. So on the central carbon there are 2 hydrogens because carbon likes 4 bonds total. And the carbon on the left has 3 hydrogens, again because carbon likes to have 4 bonds. So I'm going to highlight the 3 hydrogens on the left in yellow. I'll highlight the hydrogens on the second carbon in green. And then I'll highlight the hydrogen on the oxygen in purple. Okay, so now let's try and figure out which one of those hydrogens is the most acidic. So I'm going to ask you to pause the video, draw the conjugate bases for each different type of hydrogen leaving the molecule, and then we'll come back and go over it together. Okay, so let's draw our 3 different conjugate bases because we have 3 different types of hydrogens here. All right, so let's see what happens if we lose a purple hydrogen. So if a base comes in and takes that purple hydrogen, what would the conjugate base look like? So we would have our 2 carbons and then our oxygen with 3 lone pairs. So that oxygen is negatively charged. Now what would happen if we lost one of the green hydrogens? So we would have our purple hydrogen still attached, but once we lost one of the green hydrogens, that would leave a lone pair on that second carbon. So that second carbon would be negatively charged. And then what would happen if we lost a yellow hydrogen to a base? So we would still have our purple hydrogen. We would still have both green hydrogens, so the second carbon would be neutral. But that first carbon on the left would now be negatively charged because it's lost a hydrogen but gained an electron. All right, so we've got our 3 different conjugate bases. So now let's see which one is the most stable. Okay, so let's start with C, which stands for charge. Well, it looks like we have the same negative charge on each of the different conjugate bases, so we'll write same. So then the next step is to compare atoms. Okay, so if we lose the purple hydrogen, we have a negative charge on oxygen. But if we lose a green or yellow hydrogen, we have a negative charge on carbons. Okay, so we have a difference here, C versus O. And which one is more electronegative or more able to handle a negative charge, carbon or oxygen? Oxygen. So oxygen is more able to hold on to a negative charge because it is more electronegative. All right, so that tells us that our first conjugate base is the most stable. But then that also tells us, that the purple hydrogen is the most acidic. So it's the most likely to bond with a base and leave the molecule because the resulting conjugate base is so stable. All right. Let's do another example just to really get in some practice here. All right, so this time we'll look at a molecule with a ring in it. So this might be a little challenging to draw. Sometimes it takes practice to draw these hexagons, but we do have a 6-membered ring here. 5 of the points are carbon and 1 is nitrogen. And then we're going to specifically compare these hydrogens down below, these hydrogens up above, and then we'll also compare the hydrogen that's hanging out on the double bond. Okay, so let's highlight these in different colors because they are different. So let's highlight the one on the double bond in yellow. And then let's highlight the hydrogens down below in green. And then the hydrogens up above in blue. Okay. Oh, one thing I'm missing is a lone pair on nitrogen. We can't forget that. Okay, so let's figure out which hydrogen is the most acidic. So again, we need to draw those conjugate bases. and compare their stabilities by going through cardio. So if you want to pause the video and try that on your own first, you can. And when you unpause, we'll go over it together. All right, so let's draw our different conjugate bases after the loss of each type of hydrogen. Okay, so let's try the blue ones first. So if we lose a hydrogen up above at the top carbon in our ring, we get the following structure where we have a negative charge on that top carbon. Okay, now what happens if we lose a green hydrogen? Okay, so in that case, we're losing a hydrogen on the bottom carbon. So that bottom carbon ends up with a negative charge. And then what happens if we lose the yellow hydrogen? Okay, so in that instance, we will leave a lone pair on the double bonded carbon, and it will be negatively charged. All right, so now let's start going through cardio. So let's start with charge. So it looks like we have a negative charge on each of our conjugate bases, so those are all the same. So now we need to compare the atoms. Okay, so all of the negative charges that we can see are on carbon atoms. Okay, so those are all the same. So now we go to resonance. All right. So do any of these structures have resonance? So let's look at our first conjugate base where we lost a blue hydrogen. Is there a possibility of some resonance there? Yes. So I notice a resonance pattern. We have a negative charge next to a single bond next to a double bond, or we could also say sigma bond and pi bond. Okay, so let's show what would happen if we move that lone pair of electrons down and then move the pi bond over. Okay, so now we have a sigma bond below nitrogen and a double bond above nitrogen. And again, sometimes this takes a little bit of practice to get those hexagons just right. And then we end up with a lone pair on the carbon below nitrogen. So that now is negatively charged. Okay, and I think that's all we can do in terms of resonance structures. So we'll draw brackets around these two. Okay, let's look at the structure or the conjugate base that results if we lose a green hydrogen. Can we form any resonance structures there? Yes, we have a very similar pattern here, a negative charge next to a sigma bond next to a pi bond. All right, so what would happen if we move that lone pair up to create a double bond? We would find that this pi bond, or the pi electrons, would move up to nitrogen. Okay. Now, you might be wondering, why don't we move the pi bond up and create another pi bond above nitrogen? Well, remember, the carbon on top has two hydrogens. So if we added a double bond there, that carbon would have 5 total bonds, which would create a Texas carbon. And we don't want that. So we're not going to do that. So instead, we're just going to put the pi electrons on nitrogen. Okay, so we have a single bond now below nitrogen and above nitrogen. But we do have a double bond towards the bottom of the ring. Nitrogen now has 2 lone pairs, so it's gained an electron, which means that it is negatively charged. And I don't think there's anything else we can do here in terms of resonance, so we will put brackets around our structures. Okay, and then what about our third conjugate base where we lost a hydrogen in yellow? Does that have any resonance? Nope. We have a lone pair on, or I guess next to a pi bond, but we need a sigma bond in between those two in order to have resonance. So there is no resonance on that third structure. Okay, so that means that when we compare the 3 different conjugate bases, the first 2 conjugate bases where we lost a blue hydrogen and a green hydrogen are the most stable so far. The conjugate base where we lost a yellow hydrogen is not very stable because it doesn't have any resonance. So we eliminated the yellow hydrogen. Okay, so now we have to go back and compare our 2 structures up above that do have resonance. Which one is better? So let's do a second set of cardio. So this was our first cardio. Now we have to do more cardio. All right, so let's look at the charge. We have negative charges for both, so those are the same. And now let's look at the atoms. So the negative charge on our first structure is shared between 2 carbons. And I'll highlight those here. So the charge is shared between the top carbon and then the carbon below nitrogen. And then in our second structure, the negative charge is shared between the carbon on the bottom of our structure and nitrogen. Okay, so we have a slight difference there. So is it better to share a negative charge between 2 carbons or between a carbon and a nitrogen? So nitrogen is more electronegative than carbon. So we would prefer to have a negative charge on nitrogen, right? So that means that our second structure, where we lost a green hydrogen, is the most stable. And that's due to the negative charge being shared between carbon and, oh, it's charged, is shared between carbon and nitrogen. All right, so that tells us that the green hydrogens are the most acidic, because if a base takes one of those hydrogens, the conjugate base will be very, very stable. So this was an interesting problem because we eliminated one of the hydrogens as the most acidic first, so that was the yellow hydrogen. But then we had to narrow it down between the green and the blue and figure out which of those hydrogens was most acidic. So sometimes you have to go through a process of elimination. All right, so now let's do a challenge problem. Okay, so I'm going to give you a slightly more complex structure with 2 rings. This will also give you an opportunity to practice drawing those hexagons. You can see that mine are not perfect by any means, so don't worry if yours are a little scraggly. All right, so on the left-hand side, we're going to put a double bond to oxygen. We're also going to draw a double bond kind of in the middle there. We're going to put a methyl group, so a CH3 group, up above. We're going to add another one in the middle. And then we're going to draw a group off to the right. And that is our structure. So now, which hydrogens are we interested in? So let's draw the hydrogens that we're comparing in this structure. So we're going to look at these 2 hydrogens at the top, kind of near the top, but over to the left. We're going to look at this hydrogen down below on the double bond, and these 2 hydrogens kind of to the bottom right. So those are all different hydrogens. So let's highlight them in different colors just to keep track of which is which. Okay, so the hydrogens on the upper left are in yellow, the hydrogen on the double bond is in green, and then the hydrogens to the bottom right are in blue. All right, so let's draw the conjugate bases that would result if we lost one of each of these hydrogens. Oops, I drew my arrows wrong. They're both pointing the same direction. That's not equilibrium. Okay, so if you want to try this on your own first, feel free, and then we'll go over it together. Okay, so let's see what happens if we lose a blue hydrogen first. Okay, so if we lose a blue hydrogen, let's see, I'm going to draw this a little smaller just in case there's resonance structures, because you never know. All right, so I think that's the full structure there. So if we lose a blue hydrogen, we're going to leave a lone pair on that carbon, and that will have a negative charge. Okay, now what would happen if we lost the green hydrogen that's off of that double bond? All right, so we would leave a lone pair behind on that carbon in the double bond, so that would also be negatively charged. And last but not least, what would our structure look like if we lost one of the yellow hydrogens? Well, if we lost one of the yellow hydrogens, that carbon that they're attached to would end up negatively charged as well. Okay, so let's go through cardio. So one, let's think about the charge. Are any of the charges different? Nope, they're all the same. So next we'll move on to atom. So are those negative charges on different atoms, or are they all carbons, oxygens? They're all carbon, right? So all of those negative charges are on a carbon atom. So those are also the same. And it doesn't really matter if the negative charge is on a double bond versus a single bonded carbon at the moment. That's where the resonance comes in. So when you're looking at atom in cardio, you're just looking at the type of atom. Okay, so third, we're going to think about resonance. Okay, so let's look at our conjugate base at the top of the page. So if we lose a blue hydrogen, does the resulting structure have any resonance? Yes. So we do have a negative charge next to a sigma bond next to a pi bond. Okay, so we can move our electrons around. All right, so let's draw what that would look like. So we're getting a lot of drawing practice in this problem. Let's see. Okay, and then our oxygen is off to the left there. All right. So our pi bond now is off to the right, and then we have a negative charge on the other carbon. Okay. Are there any other resonance structures that we can form? Yes. So we have again a pi bond or a lone pair next to a sigma bond next to a pi bond. So we can actually move these electrons down and then move the pi electrons that are bonded to oxygen up. So let's see, let me make sure I have enough space here. I think I do. With organic chemistry, you always need a lot of space to draw. All right, so we moved our pi bond over, and now oxygen will have 3 lone pairs, so oxygen will be negatively charged. Okay. Now, is there any other way we can move electrons around to create a fourth resonance structure? No, if we moved those electrons back down from oxygen, we would just end up with our second resonance structure again. So there really isn't any other way to move electrons around. So we'll just put some brackets around these resonance structures. Okay, so there are 3 resonance structures for that first conjugate base. All right, so now let's see if any of the other conjugate bases can compete with that. So let's look at our second structure where we lost a green hydrogen. Are there any resonance structures there? Nope. We have a lone pair on a carbon that's in a double bond, and so we can kind of eliminate that from our list. Now, what about the structure that results if we lose a yellow hydrogen? So our third conjugate base. Are there any resonance structures there? Yes. So notice that the lone pair on carbon is next to a sigma bond that's next to a pi bond. Okay, so we can move those electrons around. And our resulting structure. Will look something like this, and the oxygen now has 3 lone pairs. So oxygen will be negatively charged. Is there any other way that we can move electrons around? No, because if we tried to move these back down, the only pi bond that's directly attached to that sigma bond is the one we already moved. So we would just end up with our original structure in that case. And this pi bond over here is too far away. There's 2 sigma bonds in between that pi bond and the negative charge on oxygen. So that's not possible. All right, so those are the only 2 resonance structures for our third conjugate base. So which hydrogen is the most acidic? The blue hydrogens, because again, there's 3 resonance structures, so that negative charge is shared between 3 different atoms, which really stabilizes the resulting molecule. Now, if we look at the structure that results when we lose a yellow hydrogen, that only has 2 resonance structures, so it loses out to the blue hydrogens. All right, so I think we'll stop there for today. Next time, we're going to go over bases. So far we've just been drawing generic bases, or Bs with a lone pair. But we'll see how we can actually choose an appropriate base for an acid-base reaction. So I will see you then.